Welcome to our Senior Engineering Project presentation. We are Team 11 from Grand Valley State University, and this is our project sponsored by Magna, an automated glass actuator memory tester. Magna currently uses a manual process to test memory mirror actuators, which involves visual alignment of a laser with distant targets. This setup is prone to human error, inefficient, and occupies valuable lab space. The smart tester on the left requires manual user input, while the target on the right requires the user to manually read the data. Both of these contribute to extra error that can be eliminated through automation. Our objective was to create an automated test platform that reduces setup time and error while accurately capturing mirror position and voltage data for quality assurance. Our solution needed to meet strict performance specs, including under 5-minute test cycles, under 15-minute test setup, precise angle and voltage measurements, and it must be portable and compact. Mechanically, we designed a mobile aluminum frame out of T-slotted 80/20 with a laser alignment system and calibration tools. The measuring stick and mirror fixtures ensure consistency with each test. Electrically, the system is powered by a Raspberry Pi 5. It controls the motor drivers and reads voltage using high-precision ADCs. A GoPro camera captures laser positions on the screen. The GUI walks users through 3 essential calibrations: camera alignment, actuator direction verification, and laser centering. These steps ensure repeatable and accurate measurements.
The first thing the user sees is the graphical user interface. The user is able to select 3 test types: for test, single target test, or manual test. The single target test allows the user to go to one desired target manually using the keyboard arrows, move to a random location, and then the system will automatically go back to the desired target and collect the position of the actuator and the angle difference. The manual test allows the user to move to a number of desired targets manually, up to 5 targets. Once all targets are reached, the system will automatically go back to each target and collect the position of the actuator and the angle difference between the set and recall values. The for test follows this for specification, reaching to a total of 17 target locations automatically. The first 4 targets are reached using computer vision to track laser color profile and go to a desired target pixel value relative to the camera and the screen locations. The next 13 targets are recall of the original 4 set targets in a specified sequence defined by the 4 spec. The user is also able to enter the part number, technician name, turn on the laser on and off, invert the vertical and horizontal directions, and calibrate the camera and actuators. Currently, we're running the for test. As we move to the screen and camera, we can observe that the laser dot is getting to the first 4 targets. In each target, the position of the actuator and the pixel location of the laser is related to the position of the actuator are stored. The position of the actuator is represented as a vertical and horizontal voltages. Once the laser hits the first 4 targets, the system switches to recall the targets based on the recorded memory voltage position of the actuator. In each recall position, the pixel location of the laser is recorded to then compare with the initial pixel location, allowing us to calculate the angle difference. Here, we're showing the electrical enclosure where we have all the electrical components involved in the system, as well as 2 fans to control the temperature inside of the enclosure. As we go back to the GUI, we can observe that the vertical and horizontal voltage values are being stored and displayed for a quick data interpretation. After each test is finished, the system stores the recorded data in a formatted spreadsheet. Once the user is done testing all the mirrors, the user can export the spreadsheet to a flash drive.
We faced several engineering challenges, including minimizing angular error, eliminating camera distortion, and ensuring the laser remained aligned. These were solved through a combination of hardware calibration tools and robust software algorithms. One example of this is the image distortion correcting algorithm, the results of which are shown below. All machining and assembly was done in-house, either at Magna or at Grand Valley State University. Care was taken to maintain simplicity throughout the build process. This allows for future repairs as well as possible duplication. The final product is compact, fully automated, and accurate. The GUI and data export functions make it technician-friendly, and repeatable calibration ensures consistent results. All project specifications were met or exceeded. The system improves testing efficiency, enhances data reliability, and meets Magna's operational needs. This system not only modernizes Magna's testing process, but also sets a standard for future actuator evaluation tools. It reduces lab traffic, eliminates subjective measurement, and outputs clean, standardized data, ready for engineering analysis or QA reporting. Looking forward, this framework can be adapted to accommodate new mirror technologies and even trailer tow variants. Thank you for watching. This project reflects the collaborative effort between Grand Valley State University and Magna Mirrors, and we're proud to contribute to advancing automotive testing.